Hello. We are continuing with our discussion on response to harmonic loading. Okay. And again, to go back to, I did end my last lecture rather hurriedly, and so I want to go back a little bit and look at the Argand diagram that I had drawn. I'll redraw that Argand diagram again for you. And I'm not going to spend any time in explaining because we've already done all of this. P naught omega bar t, P0 beta square d, then this is omega t minus theta, then opposite this is P naught d, this is omega bar t minus theta, and then at 90 degrees to that is P naught into 2 xi beta. These values that I am writing, all of them are the magnitudes of the vectors, and the direction of the vectors are given by this. Okay? And as I explained, these are 90 degrees to each other, and these three balance out P naught. Okay? So, this was the diagram, and then we went back to for me to show you that these three indeed give you balance out P naught and vectorially. Now, vectorially it is very difficult. So, what I did was we looked at just the real part, and therefore, what we saw was that this sine omega t plus this cosine omega t is equal to P naught sine omega bar t plus P naught. So, writing that properly, it becomes in this fashion. It becomes now P naught d, so that is minus P naught d sine omega bar t minus theta minus P naught into 2 xi beta into d cosine of omega bar t minus theta. Okay. Then we have plus P naught beta squared d sine omega bar t minus theta plus P naught sine omega bar t is equal to 0. This is if you look at this, these are all the projections of each vector on the real axis. That is what I have written down over here. Okay. So, this part is what we are going to see, that indeed that this is the truth. Okay. So, we had now what I will do is instead of rewriting this, I will just write down what sine omega bar t minus theta is equal to sine omega bar t cosine theta minus cosine omega bar t sine theta. Okay. So, that is the solution that you have. Okay. And cosine omega bar t minus theta is equal to cosine omega bar t cosine theta plus sine omega bar t sine theta. Okay? So, these are the expansions of these terms that we have over here. Furthermore, we see that we know that tan theta is equal to 2 xi beta upon 1 minus beta squared. So, this, as I drew last time, was this. This implies that if this is theta, this is 2 xi beta and this is 1 minus beta squared. So, obviously, this is equal to, by Pythagoras theorem, because this is 90 degrees, is going to be equal to 1 minus beta squared plus 2 xi beta squared square root. This is the Pythagoras theorem, right? If you look at this is the Pythagoras theorem. So, if we look at this, what is this term? This term is nothing but it is equal to 1 upon d. Okay? So, therefore, if you look at sin theta is equal to 2 xi beta upon 1 upon d. Upon 1 upon d basically becomes, that means 2 xi beta upon 1 over d is means sin theta is equal to 2 xi beta d. And similarly, cosine theta is equal to 1 minus beta squared upon 1 upon d. So, that becomes equal to d. So, if we substitute this back into those equations, okay, if you look at it, what happens? What we see is the following. I am going to substitute these into sine So, this is going to be equal to cosine into sine, cosine theta. So, that is 1 minus beta squared d into sine omega bar t minus 2 xi beta into cosine omega bar t. This is sine theta, this is cosine theta, and cosine omega bar t minus theta is equal to cosine omega t into cosine theta. So, that is equal to 1 minus beta squared d cosine omega t plus 2 xi into sine omega t. Okay? So, this is what we get, and substituting this into the original equation, that becomes then, it becomes minus p naught d into sine omega t minus theta. This is what I am substituting, right. So, I am substituting 1 minus beta squared d sine theta minus 2 into cosine omega t. So, that is the first one. Then the next one is p naught into 2 xi beta d into cosine omega t minus theta, which from here turns out to be equal to 2 xi beta d sine omega d plus 1 minus beta squared d into cosine omega d. And then finally, I have p naught beta squared d into the same thing that I have here, okay, 1 minus beta squared d sine omega d minus 2 xi into cosine omega d plus p naught sine omega bar t is equal to 0. So, we have to just show that this is indeed equal to 0. So, if I now look at this term, this is identical. So, now let us look at putting all the sine terms and cosine terms together. Okay. So, if I look at the sine term, I am putting together all the sine terms. What I get is put the sine terms together, it becomes 1 minus beta squared minus P naught d squared. That comes from the first one. From the second one, you get minus P naught 2 xi beta d into whole squared into this. So, it is basically two terms, and then the third term becomes plus P naught beta squared into 1 minus beta squared d squared, okay, this into sin omega bar t, and then the cosine terms, if I put them together, what I get is minus minus plus P naught into 2 xi beta d squared. Okay. Then from the other one I get minus P naught. So, P naught into 2 xi beta into 1 minus beta squared d, that is what I get cosine, and then from the other one I get minus beta squared, sorry, this is d squared, and then minus beta squared into 2 xi beta d squared P naught into cosine omega bar t. Okay. This plus P naught sin omega bar t is equal to 0. Okay. So, I have not put the P naught inside, but I will put it in. I do not worry about it, I will put that in. So, if I look at it, what I get here is the following. If you really look at it, I get, if you look at this particular term, it is 1 into 2 xi beta minus beta squared into 2 xi beta. So, it becomes basically these two, if I put them together, I get one term which is 2 xi beta into 1 minus beta squared P naught d squared, and the other term is 2 xi beta into 1 minus beta squared P naught d squared. So, that means these cancel out. That means, if you look at this, this becomes 0. Now, this is obvious, 0 into cosine omega bar t, because there is no term. So, this term should automatically become 0, and that is what it becomes. Okay. Let us look at what happens here. If you look at this particular thing, this becomes 1, it becomes minus, right. If you look at this, this is 1 and this is beta squared. So, this becomes actually minus 1 plus beta squared, which I can write it as minus of 1 minus beta squared. Okay. So, essentially what I am getting is this term, top term, becomes minus 1 minus beta squared the whole squared P naught d squared minus P naught into 2 xi beta squared d squared. Okay. I put the two of them together, plus P naught sin omega bar t equal to 0. Now, for this, that means this term, these terms together have to be equal to 0. Well, let us look at it. Okay. This term, if you look at it, basically becomes minus of 1 minus beta squared plus 2 xi beta squared the whole into P naught d squared, okay, Now, if you look at it, what is d squared? D squared is nothing but 1 upon beta squared, the whole squared, right, plus 2 xi beta, the whole squared, square root, 1 upon, right. D, if you remember, is equal to nothing but square root of 1 minus beta squared. So, if you look at this particular term, what is this term? If you look at this term, this is nothing but 1 upon d squared. So, if I take minus 1 upon d squared into p naught d squared, what do I get? I get minus p naught, and this other one is plus p naught. So, indeed this is 0. So, in other words, there is equilibrium as you see it from this particular point. Okay. So, after all that huge amount of calculation, we showed that indeed these equilibrate each other. If you look at this diagram, these three equilibrate this. Okay. Now, let us look at some interesting things. This Argand diagram will show certainly a very interesting thing. Let us take a situation where beta tends to 0, and we will assume that xi is very much less than 1. In other words, xi tends to 0 without being 0. Understand that it tends to 0 without being 0. Why? Because you do not have steady state if you have xi equal to 0. But let us say that it tends to 0. Then what happens? Let us look at this. If you look at this, if beta tends to 1, what do you have? You have p naught d. Remember that if beta tends to 1, what happens to theta? Do you remember? Let's look at that. As beta tends to 0, what happens to the phase angle? Phase angle theta tends to 0. In other words, the phase lag, if we come back to this, the lag, this theta, is for all practical purposes 0. So, then if I redraw that, what does this equation look like? I mean, what does the diagram look like? The diagram looks like this: imaginary, real, this is p naught, okay. This is, as beta tends to 0, what happens here? This becomes p naught beta squared d. So, in other words, the inertial force becomes just, and it is along this for all practical purposes, it's along this, and it is equal to p naught d. Okay. So, this is what are we saying? And by the way, when beta tends to 0, where does d tend to? D tends to 1. So, that means this one says that this is equal to no, sorry, I am making a mistake here. I made the mistake. Beta tends to 0, okay, then theta tends to 0, xi is less than 1, so xi tends to 0. So, if beta tends to 0, what happens to this term? This term disappears. The inertia disappears. Okay? Inertia disappears. What happens to this one? This is also beta, tending to 0. So, this term disappears, and what are we left with? We are left with this one, which is p naught, and d is 1. So, this is p naught. So, if you look at this, when you have beta equal to 0, theta is equal to 0, okay, then you have a situation in which this term goes to 0 because beta is equal to 0, this term goes to 0 because this term is equal to 0, theta tends to 0. So, this tends up, so this becomes this way, and what you have is, what does beta equal to 0 actually mean? Static. Omega is equal to 0, this is static condition. In static condition, what do we have? The applied force is resisted completely by the elastic force. That's static. In static, okay, the entire load is resisted by the elastic force. So, in other words, from this part, we got the situation that indeed, okay, at the static case, this becomes the trivial solution where both the equilibrating force, which is the elastic force, is P naught, the applied load is P naught, inertial force and damping force are 0. Okay? So, that is the static case, understandable, very easy to understand. Okay? Then let us look at the situation where you have beta tends, well, let us put beta equal to 1. Beta equal to 1 implies, let us see, what is delta equal to? Delta is equal to 1 upon 2 xi. We have already derived this in the last lecture, and phase angle theta is equal to pi by 2 or 90 degrees. 90 degrees out of phase. So, now let us see what does this. So, what does this look like then? Let us see. I have the applied load at P naught, that is at omega theta. Now, look at this. This theta is equal to pi by 2. So, in other words, this one which is my P naught beta squared. So, that is equal to P naught d, right. So, this is 90 degrees because theta is 90 degrees. Then I have this term, okay, where beta is equal to 1. So, this becomes 2 xi d. So, this is 90 degrees with that. So, this is P naught 2 xi d, okay, and so this is 90 degrees from that, and note that this one is 90 degrees from there. So, that means this one is along this direction and it is equal to P naught d, okay, 90 degrees, 90 degrees. So, this is theta and these are 90 degrees. So, look at the very interesting thing, and look at what d is what? D is 1 upon 2 xi. So, if I look at this, what does this become? This becomes P naught. Look at this very, very interesting thing, and that is at resonance when beta is equal to 1, resonance, the applied load is resisted completely by the damping force, okay, because it is only resisted by the damping load. That is the reason why the dynamic amplification factor becomes 1 upon 2 xi, very large, because understand, for if damping is low and that has to resist this, dynamic amplification has to become 1 upon 2 xi, so that this becomes P naught, it can resist this. And look at the inertial force and the elastic force. They are completely out of phase, sorry, not out of phase. They are 90 degrees out of phase with the applied load and the damping force, and they balance each other out. Okay. So, and note that these values will be very large because P naught d is very large. So, in other words, you have a peculiar situation at resonance that since the damping force resists the applied load, okay, therefore, the inertial force and the elastic force are very large. Okay. However, they are 90 degrees out of phase with the applied load. So, despite them being very large, all they do is they cancel each other out. Okay. And so, you have this peculiar situation where at resonance the Argand diagram turns out to be in this way, and that is the reason why, because of this, D becomes very, very large, the dynamic amplification becomes very large for small xis. Okay? Okay. So, now let us look at the last kind of situation which I will look at, which is when beta tends to infinity. As beta tends to infinity, what happens? Let us look at it. Phi tends to pi or 180 degrees, okay, and let us see what happens, and we will see what happens to D. Let us draw the Argand diagram, real, imaginary. This is P naught. So, this is omega bar t, and now phi, now this theta is 180. In other words, what I have is that my P naught beta square d is 180 degrees out of phase with P naught, because theta is exactly that term. Then this direction becomes P naught into 2 xi beta d, and note that this direction becomes P naught what? D, right. Let us look at this situation. What happens to D as beta tends to infinity? D tends to 0. That means this becomes 0, this becomes 0, okay. For all practical, it tends to 0, so they become very small. These and these become very, very small, okay. And so, let me take in the asymptote, this becomes 0, this becomes 0. And what is the resistance? Let us look at this. What is D actually? If you look at D, it goes as 1 upon beta squared. So, D goes up 1 upon beta squared. So, if you look at this, the elastic force is 0, the damping force is 0, and what resists the applied loading? It is the inertial force that balances the applied load, and you look at, because beta squared d, this goes as 1 upon beta squared. Remember, we had done all of this last time, I mean a couple of lectures ago, and therefore, what you have is, remember I said that elastic force was 0. Why? Because the applied load is completely resisted by the inertial load, and therefore, elastic force is 0. So, you see, the Argand diagram actually tells you many very interesting things about the various, what are the kind of mechanisms that you have for various kinds of situations. Okay? So, I think I am pretty much done with response of a structure to harmonic loads. Now, what I would like to do is actually look at a specific case where we are going to actually apply the response of a structure of a single degree of freedom system to harmonic loads, and this is a very two specific situations that I am going to look at, and we are going to derive the kind of let's look at the two situations. One situation is where you have a machinery which is connected to a floor, okay, and we say that, look, the floor is subjected to a vibration, and the vibration is given by okay. So, the floor vibration, and this is a very sensitive equipment. sensitive equipment. What we want to say is that, look, what we do not want to transmit this to this sensitive equipment. In other words, what I am saying is that the acceleration that this sees, the total acceleration that this sees should tend to 0. Okay? That is my problem. The problem is that this is vibrating. The base of the equipment is vibrating. We can't stop that vibration. That vibration is happening. What we want to do is isolate, and this is known as isolation. We want to isolate this equipment from its base. Okay? So, this is known as something called as base isolation. This is one problem. Okay? The other problem is just the reverse of this. What I have is, I have a machinery. A machinery is transmitting a particular force to the floor. And what I want to have to happen is that the force transmitted to the floor. So, the force transmitted to the floor, okay, I want that to be, for all practical, 0. So, even if what I am trying to say, because you see, if these are two flip sides of the coin. Here I have a situation where the floor is vibrating and I want to isolate the sensitive equipment from that floor vibration. The other situation is a machine. So, this is a machine vibration problem, and I want to this machine, because of its operation, is going to have a force acting on it. Okay? What that force is will come, we can discuss that later. But you know, when you have a rotating machinery, because of an imbalance of forces, you actually end up getting forces which are making it vibrate in this way. And what I want to do is, okay, let the machine vibrate, but I do not want the floor to vibrate at all, because after all, on the floor are some other kinds of things where I do not want to transfer this force. So, this is actually a force transmissibility problem. So, this is a base isolation problem, and this is a force transmissibility problem. And in both cases, let me say that this is F0 sin omega bar t. So, I will assume that both the excitations, here the floor excitation is given as a harmonic, and here the load from the structure is given as F0 sin omega bar t. So, let us first look at how we can solve these problems. So, for this problem, let us start first with the base isolation problem. Okay? Well, let's not. Let's start with the force transmissibility problem. That's a simpler problem for us to understand, because for the base isolation problem, I'll have to start defining some new parameters. So, before I do that, I will actually look at the force transmissibility problem. Okay? And if I look at the force transmissibility problem, it becomes the following. I have an equipment which is transmitting a force F of t is equal to F0 sin omega bar t. This rigid machine is connected to the floor through some spring and dashpot system, and what I want to do is I want to figure out what this floor, I will call this the transmitted force. What is this equal to? Well, if you look at this, this is a block, machinery block of mass m. It has K and it has C, okay, a spring and a dashpot connected to the floor. So, what is this problem? This problem, if you look at it, is nothing but m u double dot plus c u dot plus k u is equal to f naught sin omega bar t. This is a single degree of freedom problem. Okay. Now, the question is, what is the transmitted force? The transmitted force, if you look at it, is nothing but f of transmitted force is equal to k u plus c u dot, nothing else. There is nothing else to it. Okay. So, now the question becomes, what is k u and plus c u dot equal to? That is all I need to do. Now, note that I have already solved this problem. Okay. So, I am not going to resolve the problem, I am just going to write down these terms, and let me write down what these are. What is u from this equation, u of t? Note that I am always looking at steady state. There is understand that if there are no initial conditions, in other words, this load has been there for all times, there is no initial condition, then the response is only the steady state, and the steady state response becomes what? F naught upon k into d sin omega bar t minus theta. That is my u of t. And what is my u dot of t? U dot of t becomes f naught upon k d omega bar cosine omega bar t minus theta. Okay. So, once I have these, I plug these in, and my transmitted force becomes what? My transmitted force becomes very simple. F of t is equal to k of u 0. So, that is equal to f naught k d into k sin omega bar t minus theta plus c into u dot. So, that is equal to f naught upon k d into c omega bar cosine omega bar t minus theta. So, if you look at this, what does this become? K cancels out. So, this becomes f naught d sin omega bar t minus theta plus f naught. What is c omega bar upon k? We have already seen it, 2 xi beta d cosine omega bar t minus theta. Okay. Now, this is sine into x, this is cosine into x. Note that both of them have omega bar t minus. So, this is sin x and this is cosine x. So, therefore, if I have sin x and cosine x, what is the amplitude? It is very easy. The amplitude, the f t 0, which is the amplitude, is equal to what? It is equal to f naught d the whole squared plus f naught 2 xi beta d the whole squared square root, right? That is the amplitude. I am only interested in the amplitude, because understand that the time variation is not of importance to me. I am interested in the this thing. And if you look at this, if I rewrite this, this becomes essentially equal to f naught, and the d squared term goes out. So, this becomes d inside, and the inside basically becomes 1 plus 2 xi beta half. Okay. So, this is the amplitude of the force transmitted to the floor, and this is the amplitude of the applied force. So, if I define a term called the transmissibility ratio, and the transmissibility ratio is defined how? The transmissibility ratio is defined as transmissibility ratio is equal to f t 0 upon f 0, which is equal to what? D into 1 plus 2 xi beta whole squared square root, and incorporating d inside, the transmissibility ratio essentially becomes 1 plus 2 xi beta the whole squared plus 1 minus beta squared plus 2 xi beta. This becomes the transmissibility ratio. Very, very interesting. Let us see something. Let us plug in beta. In other words, if you look at this, for small zetas, this almost looks like the dynamic amplification factor with an additional term on the top. But let us look at a particular situation, beta is equal to 2. If beta is equal to 2, then what do I get transmissibility ratio to be equal to? Well, 1 plus, this is beta 2 xi beta the whole squared. So, beta squared becomes root 2 into 2. So, this becomes what? It becomes, well, let us look at it. This is 2 xi squared. So, 2 xi squared is 4 xi squared. 4 xi squared into 2 is equal to 8 xi squared, and at the bottom I have 1 minus, by the way, root 2 to 2, so this is 2 the whole squared plus, well, let us look at this. This also becomes 8 xi squared, okay, square root. 1 minus 2 is minus 1, whole thing squared becomes 1, minus 1 squared is 1. So, this becomes 1 plus 8 xi squared upon 1 plus 8 xi squared. So, transmissibility ratio is 1. At beta equal to 0, root 2, transmissibility ratio is 1 irrespective of xi. Look at beta equal to 0. Transmissibility ratio is equal to beta equal to 0, this becomes 0. This becomes 0. So, it is 1 upon 1, transmissibility ratio is 1. Okay. Let us look at how the transmissibility ratio looks. If you look at this, this is the transmissibility ratio TR, which is the transmitted force amplitude upon the applied force amplitude. And if you look at it, at beta equal to 0, this is 0. Okay. At root 2, this is 0. Okay. And between 0 and root 2, transmissibility ratio is greater than 1. In other words, for between 0 and beta root 2, transmissibility ratio is greater than 1. Okay. And for beta greater than root 2, transmissibility ratio is less than 1. Now the question becomes, I want to ensure, so I want to design a support system, the machinery, I want to design the support system, the foundation of the machinery such that the load transferred to the base is 0. So, I have to design a system. Let us look at, to make it 0, what do I need? Let us look at this, very, very interesting. You see how this goes? When you go, you want it to become low, okay? You want to take it to 0 as fast as possible. What do you have to do? You have to ensure that beta is as large as possible. Beta is large, and let's look at something very, very interesting, that actually damping, note that in this situation we always saw that low damping meant high transmissibility ratio and high damping reduced the transmissibility ratio. So, whereas when you go beyond root 2, okay, damping actually harms, because the lower the damping, the faster it goes to 0. So, in other words, ideally speaking, what kind of a system would you like to ensure that the load transferred from the structure to the foundation is as low as possible? It would imply that beta has to be large. What does beta equal to large mean? Understand something. Let's define it very carefully. In other words, what are we saying? Beta has to be large and xi should tend to 0. If beta is large, xi tends to 0, this implies transmissibility ratio tends to 0. That is what we have seen from this. If you look at this, right, beta large, xi 0, it goes to 0 fast, transmissibility ratio. Okay. So, what does beta large mean? What is beta? Let us define it. Omega bar upon omega is beta. Now, you see, this excitation frequency we can't do anything about, because that is the frequency that is coming from the machinery. I can't change the frequency of the machinery, because that is the operating frequency of the machinery, right. So, omega bar is fixed. So, to get beta large, what do I need to do? I need to make omega tend to 0. What does omega tending to 0 imply? Note that the machinery mass is a fixed. So, that means K tends to 0. That means soft springs, no damping. That is what you have to do. That means you need to put the machinery on soft springs with no damping to ensure that very little gets transferred to the floor. Now, see, this is where I am trying to solve what problem? The dynamic problem. But what other problem do I have? Note that if I make the spring too soft, what happens? Well, the mass, the machine has weight, and if I make that so soft, okay, what is going to happen? The spring is going to bottom out purely because the weight itself takes it down. Soft spring means what? Very flexible spring. If I have a particular weight and I have a very flexible spring, it is going to sit down. So, you see, there is this very, very key problem, that sometimes in trying to solve one problem, we actually create another problem, and that is a classical situation. So, please understand that the spring has to be hard enough to be able to take the weight and not bottom out, because the spring has a certain amount of play, right. So, it shouldn't bottom out because of the weight. So, it should be hard enough for that. However, it should be soft enough such that beta is large. So, this is a design is always an issue of trying to optimize how you want to do. So, now the question then becomes that, so therefore, ideally I would like beta to be greater than root 2, ideally. Suppose because of the static problem, my K value of the spring needs to be such a value such that I cannot, for the operating frequency, ensure that beta is greater than root 2. What do I do then? What is the design problem then? Then you look at it, come back to this. In other words, I cannot be in this domain. If I am in this domain, if I can remain in this domain, I prepare as soft a spring as possible with no damping. But suppose I have a situation where I can't be in this zone because of the value of omega being such that beta is less than root 2. Then what do I have to do? Then the whole problem changes. If I cannot ensure that beta is greater than root 2, I cannot ensure that there is no load transferred. I cannot. Because look at this situation. I can only ensure that no load if I am in this zone. If for operating reasons, I have to be in this zone. Note that the minimum value that I can transfer is the static value of the load itself. In other words, the minimum value of transmissibility that I can keep is 1. I cannot take less than 1. And what do I do in that situation? In that situation, I have to over damp. In other words, huge damping, build in huge damping into the system such that the transmissibility ratio remains as close to 1. In other words, look at it. Almost make it critical damping to ensure that you see 0.7 and 1 are very close to each other. 0.7 is under critically damped, 70% damping. So, 70% damping, you need to introduce huge damping into the system to ensure that transmissibility ratio remains low. Okay? So in other words, the point that I am trying to make is that a design problem is really you are trying to weigh two. Ideally, I would like to make the springs as soft as possible, then I don't put damping in at all, and transmissibility can be as low as possible. On the other hand, for operating reasons, if beta cannot be less than root 2, then I have to put in a design where I have to put in huge amount of damping and keep it as soft as possible. In other words, as close to root 2 or make it completely rigid, so that transmissibility comes close to 1. Okay, so I think that is the force transmissibility problem. We will look at the base isolation problem next time, and we will see that essentially that problem also mathematically boils down to the same problem. Okay? And after that, I am going to look at to see how the response of a single degree of freedom system can be used to get omega and xi. I did talk about it a little bit, but I will spend a little bit more time talking about how to get the dynamic characteristics of a structure from harmonic forced response values. Okay? Thank you very much. See you next time. Bye.